All right, so let's do part 2 of section 2.3. We have learned a lot of nice and well-behaved properties of limits, right? And everything was very straightforward. And now at this point, we will do, let's say we have done 5 problems so far. Let's do the 6th one, which is now going to be a piecewise defined function. 4x minus 3 if x is less than 2, and x minus 3 square if x is greater than or equal to 2. Find one-sided limits. And if the limit exists, let's find that too. Okay, so how do you do this? I can't just plug in, oh, I forgot, at equal to 2, right? So 2 is the point where a gap may happen here, right? So a problem like this, it may be just really helpful if you graph these at the beginning, okay? Because being able to visualize this certainly helps. All right, so here's the point 0, the origin. If x is less than 2, you notice here having a graph paper is actually a very nice thing. So you may actually want to get some graph paper or get a tablet with a graph paper background, and you can graph these much easier. All right, now the first part says 4x minus 3, 1, 2, 3. So the y-intercept is -3. It goes up by 4 each time. 1, 2, 3, 4. So it looks like x is y is approaching 5. I do this. Yep. Okay. So that is what the here. Let me go ahead and extend this a little bit. You can do this on your own. You know how to graph a line, right? So f is equal to 4x minus 3 as long as x is less than 2, strictly less than 2. So there should be a circle here, right, where it's supposed to be 2, 5. And by the way, when you plug in 2 here, you get 8 minus 3, which is 5. So this is the correct value. When x is greater than 2, then the function is going to be x minus 3 squared. Now, x minus 3 squared is going to look like this. It's a parabola centered at, or whose vertex is at the point 3, 0. And so it'll go like this. Okay. Now, if I were graphing the parabola, this would be like this, but I don't have to do that part because remember, this only applies, the x minus 3 quantity square definition only applies when x is greater than or equal to 2. So we don't even have this part here. We do have a black dot here at 2, 1, because when x is equal to 2, you have -1 quantity squared, which is 1. So the graph of this function looks like this. Remember, this is one graph, okay? And it's one function, f, which happens to have 2 parts, piecewise defined. Okay, so what is the limit of fx as x approaches 2 from the right? Well, you can easily see that is 1, because as x approaches 2 from the right, f of x approaches 1, according to the second part of the definition. Now, as x approaches 2 from the negative side, I have to use the first part because x is always less than 2 as x approaches 2 from the left. And so approaching this, you'll go up to 5. And therefore, what do you know about the limit? Oh, by the way, I refer to this as the right side limit or right-sided limit or right-hand limit or right-hand side limit. This as the left-hand limit or left side limit or whatever. Officially, the book, the OpenStax, will not use any of those terms. They will say this is the limit from the right and this is the limit from the left. That may be a nice and simplified way of referring to these. Now, the both-sided limit, which is the limit of fx at 2, what? Does not exist, precisely because these are 2 different values. All right, so Sometimes this happens. Now, when the limit does not exist, you shouldn't just say limit does not exist. You should actually explain why the limit does not exist, justifying your answer, as I just did here. Okay, it is important for you to show the two limits, the limit from the right and the left, and to show that those are different, and therefore, by the definition of the both-sided limits, that limit does not exist. Okay, number 7, the limit of x plus 2 over x minus 1 square as x approaches negative 2. All right, so is this one of those cases where the denominator has a point, so the function is not defined at 1, right? So you could sort of see the vertical asymptote. Okay, but don't be deceived by that fact. And this is correct. This function does have a vertical asymptote at 1. But remember, we're trying to find the limit at x is equal to negative 2. Okay, well, that's going to give this 0. But the denominator is non-zero. So negative 2 minus 1, that's negative 3 squared is 9. So here, because the rational functions are continuous at every point where it's defined. That's something that you will learn later. But if you can plug in, go ahead and plug in. 0 over 9 is 0. Okay, so that is actually the limit of this function. That is the correct answer. By the way, the question would be very different if I ask you for the limit of the same function at 1. Okay, so now what we have to do is to work harder. All right, so what happens? Well, again, as x approaches 1, x minus 1 square approaches 0, right? And in fact, it's always going to be positive. Yes, it is getting closer and closer to 0, but remember, we allow x to never reach 1 precisely. So this thing is going to be either positive or negative, depending on which way you approach 1, which side you approach 1 from. Okay, so this could be positive or negative, but because you are squaring that number, the denominator will always be positive. It approaches a 0, but so it becomes a very, very small number approaching 0, and it's going to be positive. Now this thing, x plus 2 near 1 is going to be close to 3, right? So it's going to be, so this is going to be close to like 3 over a number that's very close to 0, but always positive. Now again, I wouldn't write this because that's not official. This is just a note I'm taking, making for myself. Having seen this, you know that this blows up to infinity. Okay, so you could say this answer is going to be positive infinity. So the idea is around 1, you are going to see a graph just approaching infinity like that. And so that is the answer to this question. Okay, now having answered this, let's erase this obscene language like 0 in the denominator. Okay, so that's the answer to that question. All right. I should say one more thing here before the section is over, 2.3. There is one more important concept in this section, and that is the theorem. Okay, this is a helpful theorem which will help us, which will be valuable in giving us a pretty nice and very important limit, which we will talk about. All right, and the theorem that we will be using is called, let me give you the official name first, the squeeze theorem, more affectionately known as the sandwich theorem. You agree, this sounds better, right? I mean, sandwich sounds much more fun than squeeze theorem. Okay, so what is that? Well, all right, so this is the sandwich idea or the squeeze idea. Let's say you have 3 functions. Okay, so you have fx, gx, and hx. And you know that fx is always less than gx, or less than or equal to gx, which is less than or equal to hx. So here is the given. If fx is less than or equal to g of x, which is less than or equal to hx on an interval containing a, I should say an open interval, just for a reason which I'm not going into yet. But it's important to have this open interval that contains a, containing a. All right, so if f is less than or equal to g, which is less than or equal to h on some open interval containing a, and if the limit of f of x and the limit of g of, h of x, the top and the bottom of these, is equal to L, all right? So this is going to L, and this is going to L. I said L, not with the H in front, okay? If this is L and this is L, then guess what? The limit of g of x, which is the function in the middle at A, is also going to be L, because that's squeezed in between this and that. So the point is this and this, I mean, the picture is not correct. You know, this is just showing that f is less than g, which is less than h. But if these two functions both approach L, the same value, then g, which is sandwiched between these, will also approach L. It makes sense, right? I mean, if h is the top piece of the bread and f is the bottom piece of bread and g is your ham or egg in the middle of, oops, what happened to the ham and egg? If you have something in the middle of it, and if you bite this, you know, here's your teeth, the top teeth, here's the bottom teeth. If you bite this, g is going to stay between h and g, and as these approach L, then the middle one also has to approach L. So that's the idea of this squeeze theorem or the sandwich theorem. There's also a proof because, again, this is a theorem, right? And so that is the squeeze theorem. All right. Now, here's an example of how you may want to use this. Find the limit of x squared sine of 1 over x as x approaches 0. Okay, now this is a hard question. We can't use conjugates or factoring or anything, obviously, right? Now this thing goes to 0. Now remember this evil function, the sine of 1 over x, that's the one that kind of goes like this as it approaches 0. It oscillates between +1 and -1. And so the limit doesn't exist here. But this thing is going to try to make this, you know, smaller and smaller. Okay, so the again, I'm not going to give you the answer to this question immediately, but think of a function that is smaller and bigger than this. Okay, so now you know that the sine of x or sine of anything, maybe I should say, note that the sine of anything is at most 1 and at least -1, right? So it's always going to be between +1 and -1 for all values of x. So this thing has an upper limit and a lower limit. And thus, or therefore, okay, -x squared, replace this by -1. Or I can just multiply this by negative, or the x squared. Now, by the way, x squared is always positive as long as x is not 0. So when you multiply an inequality by a positive number, the inequality does not change its orientation, right? Its direction. So by multiplying by x squared, which is positive, you get -x squared less than or equal to x squared sine of 1 over x less than or equal to, and if you multiply this one by x squared, you get that. Right? This is true for all x. See, the hard part of applying the squeeze theorem is to find f and h, the two pieces of bread. Those two things, one should be the upper limit, and the other should be a lower limit of the function that you are considering. But in this case, we were able to find that because this function here, which is this thing here, is always going to be between negative x squared and positive x squared. Okay. Now, the limit of negative x squared as x approaches 0. Now, this is a polynomial. Just plug in, right? And then this, the limit of x squared as x approaches 0 is also 0. So this is going to 0. This is going to 0. Guess what? Sandwiched between those two functions is x squared sine of 1 over x, which is a terribly behaving function. But this must go to 0. And therefore, the limit of this wild behaving function is actually quite tame, and it's equal to 0. Okay, you can actually figure out the graph of this function. Remember, sine of 1 over x looks like this. Okay, but remember, it's going to be bounded by x squared. Now, x squared goes like this. That's x squared. Negative x squared goes like this. All right, remember, this is sandwiched between this function and that function. And so the graph of this function, if you do this, is going to be like this. It still oscillates back and forth, okay? But right here, it's actually going to go to 0. And you can get this limit using the sandwich theorem. Now, you are not going to see too many problems like this because it is challenging to come up with that f and h to sandwich the middle function by, but be aware that this kind of thing exists. Okay, lastly, I want to give you two important limits, which is not so easy to obtain. And in fact, the first one requires or uses the sandwich theorem or the squeeze theorem. But these two will be quite useful when we try to find or trying to do a calculus on trig functions like sine and cosine. All right, so the first one is the limit of sine x over x. Now we have actually seen this, okay? But we didn't use the graph or we didn't use the graph. We used the XY chart to study this. When you do sine x over x as x approaches 0, we saw that this limit approaches 1. Sorry, I should not say the limit approaches 1. I hope you caught my error. The limit doesn't approach 1. The limit is equal to 1. This function approaches 1 as x approaches 0, but the limit is equal to 1. And so that is a correct statement. Also, if by the way, if you try to plug in 0 here, you get 0 over 0. Again, that's not acceptable. So you have to create, come up with a different way to find this. And there is a way to do this by the squeeze theorem. I'm going to include this in the optional third part of this 2.3 video. So you can look at this. And in fact, you should, because this is very elegant, a great use of the squeeze theorem. If you really want to excel in calculus, if you want to be a good student, if you want to get an A because you really want to have full understanding, you really should look at that next segment and optional part 3 of section 2.3 video. All right, the second one, the last one I'm going to tell you about is this other one, which is 1 minus cosine of x over x as x approaches 0. Now again, remember cosine of 0 is 1. So this is 1 over 1 divided by 0, which is 0 over 0. We don't know what that is. First time 0 over 0 gave you 1, but this time it's going to give you the limit of 0. And that's actually not by the squeeze theorem, but by using the first, this result, okay? So these I will explain in the third and optional video for section 2.3. And this actually should be good. Now, next we should, after this extra one, we should go into section 2.4 and study continuity. All right.